Welcome to part 2 of my presentation on Introduction to Vehicle Crashworthiness that I presented to Global Automotive Management Council in April of 2021. I already shared the part 1 here, so I'd like to go through the part 2. And part 2 is primarily focused on vehicle design for crashworthiness. And I think the target audience here is obviously the engineers who work in that area with a bit of general information as well. Now, we engineers, whenever we are designing something, we need some standardized modes or test modes to check our design, what to design it for and how is it doing. We need to do that part of our engineering work. So we need some standard way of testing our design, and we need some measurements to assess how we are doing in those tests. So I'm going to briefly review those two areas and then move into the new challenges that we are facing with the battery electric vehicles. We have few really good challenges there to overcome with lithium-ion batteries, the protection of the battery and the vehicle, and then just a brief review of what we know from today's vehicle performance in the field. So these are the 4 segments we are going to go through here in a short period of time. This is basically a pretty, I would say, old general knowledge. For vehicle crashworthiness, we typically impact the vehicle in the front, in the side, in the rear, plus few other additional modes also we have, but these 3 are the main ones. To give a little more information on the front, what is front impact is one of the test modes. There are a few others as well. We launch the vehicle, for example, against a rigid wall, measure the performance of the vehicle, and also we have instrumented dummies where we take measurements inside that instrumented dummy to understand what is the response of the dummy. Side impact, it could be a vehicle impacting another vehicle from the side, or it could be a moving deformable impactor impacting on the vehicle. There is also another test where vehicle is launched against a rigid pole and we measure the performance of the vehicle and the instrumented dummy in it. For rear impact, we can have one vehicle impacting another vehicle, the rear end of the target vehicle is impacted, or we can again have a moving deformable impactor coming and impacting the vehicle. Primarily that crash test at the high speed mode has been focused on the protection or the assessment of the integrity of the fuel system, the fuel tank and fuel lines, etc. We also do some structural crashworthiness tests or structural resistance tests on the roof structure or the top head of the vehicle. It's a quasi-static test. We take a rigid plate, apply a continuously a moving plate against the vehicle and measure the strength or resistance of the vehicle. So we have the crashworthiness test in the front, on the side, on the rear, on the roof. The requirements that we measure and try to meet, those requirements may apply to some vehicle system level performance or to the instrumented dummies, what we are calling here occupants, or to both. Depends on what standard or regulation or assessment method we are trying to follow. So I'm going to briefly review some of these here. There are too many to cover in a short presentation here. Just to give you a few examples, I'm just showing here one test video of a front impact test against a rigid wall, video collected from the NHTSA website. There are lots of videos to watch there, plus also there are a lot of public domain videos in YouTube to watch. In this test, obviously we have seen in the video, we have the instrumented dummy and all other vehicle systems deploying dynamically during this crash event. In video, it looked pretty slow, but it is a very high-speed event. Within 100 millisecond or 0.1 second time duration, the whole event is over. Okay. Looking into the measurements that are typically taken in these instrumented dummies, we take some measurements in head acceleration, some load cells taking forces and moments in the neck. Then there are some measurements in the chest and femur and tibia, etc., in different parts of the dummy. We also have some other measurements taken by the vehicle system, like restraints, control modules, and etc. But those are not directly visible through the data channels that are reporting the instrumented dummies. FMVSS requirement as of today and the new car assessment programs in the US, those are primarily focused on the instrumented dummy responses to understand the crashworthiness of the vehicle. In those tests, there are also instruments in the vehicle structure. For example, we can see what is the deceleration in the vehicle structure during an impact test, like a front impact test. But those are not part of the FMPS's assessment metric. Those data are there, and if you are interested, you can download a lot of data and learn from it as an engineer. However, you don't have to do all by yourself, because researchers are also doing similar things, and you can find a lot of public domain information to understand what is going on in the industry. And here is a good reference I'm citing here. They looked into several hundred vehicles over many years, and this is, for example, the measurement. All these light blue lines are showing the measurement of deceleration in the body structure during a front impact against a rigid wall. Also, the attempt has been made to represent some kind of idealized average response of all these variations we see from many different vehicle designs. At the end, the paper recommended, for example, or summarized all these results with two, you can say, idealized pulse definition for the average of all, and the top 10% means the highest amplitude ones. Now, as an engineer, you can use those ones for some engineering assessment and understand what to design things for. But these are the average responses or some top 10%. These are not vehicle specific performance that you will be interested in if you're working in real vehicle design. But those things can be used to understand what kind of performance we are looking for in a vehicle in average sense. For example, if I look into this first stage of this pulse on average, and I take a 2000 kilogram vehicle, for example, then this pulse multiplied by the mass of the vehicle will tell me how much resistance my front end structure needs to deliver. And this is 330 kilonewton force. Structure will have to survive dynamically to deliver that kind of deacceleration in the vehicle. The ultimate objective is to deaccelerate the vehicle and stop it gently. And then restraint system will take care of the occupant response management inside the vehicle. Now, if I know the force target that I'm trying to define from here, we can even take it down to the component level of the structural design, and we can use some empirical formula. Again, I'm just giving one reference here. There are a few others like that. And with that empirical formula, with a given force target defined, we can design the component that can approximately meet that kind of performance target. So that's an engineering definition of this problem description. We can take this step further. We can do finite element analysis and tune the design so overall system will work together. But at the low component level, this is how the relationship is there from component design to the overall vehicle performance. We can also take a step further now to the rear end of the vehicle, which is delivering a much higher resistance. We can again define a force target, and we will have to figure out how that resistance will develop at the front end of the system at the late stage of the impact event. One other thing that happens during this crash response is that this compartment of the vehicle is not rigid. It has some deformability in it. And if we look into that deformability, it will have some motions like that. How do I know how much it is going to intrude into the compartment? That measurement we can take from some other analysis, which we are calling the dynamic crash. We can just double integrate the pulse with the initial velocity taken into account. And then we can just plot here showing the pulsar acceleration against the double integrated acceleration response. So basically we are saying the dynamic crash. It is nothing but the translation of this monitoring point towards the front against this rigid wall, keeping it as zero reference. You can say it is a total compression of the system. And that's what we're calling the dynamic crush. Now, if I know how much deformation space or crush space I had in the front, I can subtract it from that calculated value, and that is my approximate intrusion into my compartment. FMBSS or NCAP, those test assessments criteria don't look into that measurement for any kind of performance measurement. However, if you look into IIHS, Insurance Institute for Highway Safety, they look into this residual intrusion after the event. Statically, they have the vehicle reference system. They will be monitoring certain points, and they will be saying, compared to the design position, how much those points have come inside the compartment, and they assess the vehicle performance with those measurements against some criteria to be good or acceptable or marginal or poor. Now, question may come to your mind, which comes to my mind as well. What is the relevance of those measurements against the occupant safety and the vehicle crashworthiness? Hard to find very scientific data with black and white relationship between the intrusion and the occupant performance. The best reference I can give to you is it can be concluded that the risk of injury generally increases as the intrusion value goes higher. And here is the reference. Maybe we can do more research, or the research community can do more work to really identify what values of those intrusions are really critical, and do they have any relationship to the occupant injury numbers or safety risks. They are for a certain values and not for other values. Some research was done, obviously, and that's why these assessment criteria have been established, but obviously more research can be done, so those more focused and I would say value-added research can drive the engineering development in a more meaningful way in the future. But we work with what we know today. Moving on to the side impact, again, I just share one test video from the NHTSA website. This test is being done, as you are saying, with a moving deformable barrier, with obviously mounted on a rigid frame, and there is impacting on the vehicle, and the vehicle is getting accelerated laterally and moving away. Inside the vehicle, we will again have some instrumented dummies, and there will be measurements taken inside the different parts of the dummy. Here, this is just you can say engineering term, not necessarily very objectively defined, that we are measuring the velocity of the impactor and the velocity of the impacted vehicle. So impactor initial velocity is deaccelerating, and the impacted vehicle laterally at zero velocity, and it is increasing the velocity. And we are calling that as the vehicle pulse. But we don't measure obviously the velocity directly. We measure the acceleration, and then we translate it to the velocity. So here again, the same reference I cited earlier, it is taking the average of the many tested vehicle accelerations and reporting what is the average acceleration it is seeing in the impacted vehicle, and also the top 10% response, in case you want to use those things for some future engineering calculations to understand what we are designing it for. You can use some of these values like this average pulse curve, and this is the acceleration value. If you know your target vehicle mass, you can translate it to an equivalent force, saying this is the interaction force that is coming from the interactor to the impactor vehicle to the impacted vehicle, and that the impacted vehicle will have to register to accelerate and move away. We can take this analysis a bit further. We can look into the translation or motion of the impactor and the relative motion of the impacted vehicle, and we can even calculate how much is the intrusion happening inside the deformable vehicle that is being impacted. For that, we can use the principle of momentum, and we can find out really what is the equilibrium velocity between these two bodies that are happening from conservation of momentum. And with some calculations, we can also figure out how much is the intrusion that is happening in the impacted vehicle. It's just to give you an idea of typically how much you can expect, 340 millimeter from average sense. But again, stepping back to that slide, FMBSS and NCAP assessments do not use those intrusion values as performance metric. But if you look into, again, IIHS, they do look into the intrusion during site impact. It's a different test setup, different everything, but the concept of intrusion is being used to assess the crashworthiness of the vehicle. In summary, what it means is that if you take the driver position as the reference, the post-test position of the impact site, which is shown by the black line here, the further it stays away from the driver center line, the better it is. And depending on that measured position, vehicle is given a rating of green as a good or acceptable or marginal or poor. So again, it is based on some research of A to B comparison. And personally, I think that there is still opportunity for more research to have better objective measurements of such structural performance and their relationship to the ultimate occupant performance, which is what we are really supposed to deliver. One other test, which is even more severe than that deformable side impact test, is the pole impact test. When I say more severe, it is very locally severe to the vehicle because it's a pretty localized impact, a rigid pole, and the vehicle is impacting on it laterally. That reference I cited already twice, that again gives you pretty good reference data from many different vehicles. What they mean by conventional vehicles mean the vehicles that are having internal combustion engines. And if you take the average of those pulses means the lateral acceleration measured in the impacted vehicle. And if you take that response as an average sense in the fleet, you can again convert it to an equivalent force that the vehicle structure will have to resist during this impact event. So 245 kilonewton for a 2000 kilogram vehicle mass. We can even take it a little further. We can do this again, double integration of this pulse, and we can even find out how much intrusion is happening during this pole impact to the vehicle. And you are seeing about 16 inches or 400 some millimeter of the intrusion happening in the vehicle structure during this event. Then one other structural crashworthiness test that we work on, or the vehicle structure engineers work on, is the resistance of the roof structure under a rigid plate continuously moving quasi-statically against the vehicle upper structure. And there are certain targets to measure the resistance of the vehicle roof structure against that quasi-statically moving plate. Like if it is FMBSS 216A, the requirement is that resistance should be 3 times the weight of the vehicle. If you look at the IIHS rating, then they are required to be 4 times or more than the weight compared to the weight of the vehicle to be good rated. And then they have other gradation of the rating. As I mentioned, this is a quasi-static test. We have a rigid plate moving at a very slow rate and compressing on the vehicle upper structure and measuring the resistance. So if quasi-statically the vehicle structure is delivering that kind of resistance, how much does it really translate to as a dynamic kind of impact if we want to imagine a dynamic impact on the vehicle roof structure? Again, I think there is plenty of scope for research to understand what does it mean in real life with a roof structure design of that strength. What does it do in real life? It is very hard to find much research on it, but I try to do a little elementary research based on my structural dynamics background, that if I have a spring mass system and I apply an impulse on it, and I can measure the response of my spring mass system. So if I apply a sudden impact, which is, say, this impulse is 1, amplitude 1, then a spring mass system, depending on a spring property, it will have different amplification, but the maximum amplification it can have is 2. So what we can estimate is that if statically I am applying a force of certain amount 1, dynamic amplification of the system or the resistance or force in the system could be up to 2 times. So if I am statically measuring the strength of the vehicle to, say, 5,000 multiplied by 3, 15,000 pounds, that means dynamically the structure will be able to resist at least up to 2 times at least one time up to two times that measured static force. So dynamic resistance capacity of the structure is more than the statically measured force. So a vehicle structure designed for 3 times or 4 times the weight statically, dynamically could be up to 6 to 8 times stronger. That's my point here in summary. Do we need to design the structure to that level of strength? And what benefit does it deliver to the overall crashworthiness of the vehicle? I do not know, but I think we can all do more research and learn about it in future. Moving on now to the FMBSS 301, which is basically a fuel system integrity test. It doesn't have any other measurement metric there. And because there are not other measurement metrics, no instrumented dummy, obviously, no other structural pulse measurements even there. So it's hard to find any other structural response data from even those tests that are accessible in the NHTSA website. So there is not much light I can share on this problem with analysis, because it is primarily a fuel leakage test, and there will be some measurement of the fuel leakage if there is any, and the performance report will be there without any other structural measurement that I can find. Moving on to the next phase, electric vehicle safety or EV safety. This is FMBSS 305. FMBSS 305 includes those rear impact tests from 301. It also includes the side impact tests. It also includes the front impact tests against the rigid barrier and the angular barriers. All these test modes are included there, and there are some performance criteria defined for the electric propulsion system, which I just give a brief summary here. And there are several measurements taken. Again, there is no occupant measurement. There is no structural crashworthiness measurement directly, but indirectly, structural crashworthiness is reflected through those measurements that I am highlighting here with color. Electrolyte spillage. How much of the electrolyte spillage is allowed? Assuming that these are hazardous chemicals, so we want to limit how much spillage should be there. Retention of the propulsion batteries. The battery should be retained to some extent, means retain some of the attachments to the vehicle body structure. And this high voltage battery system, which stores a very high amount of electric energy, that has to maintain a certain level of isolation, so the entire electric vehicle structure will not be, say, in the same electrical line with the battery system itself. So it must be battery system isolated after the crash event or during the crash event as well. So those measurement metrics are there that indirectly tie to the structural crashworthiness of the vehicle design. And that's what the structural engineer or crashworthiness engineer are facing today's challenge, to meet those indirect requirements plus also design a structure efficiently. And that's where I'm going to focus on for the rest of my presentation. Now, there I just mentioned about the regulatory part of FMBSS 305. But we also test our vehicle for public domain assessments like NCAP assessment, which is focused on the occupant or instrumented dummy measurements. We have IIHS side impact test that looks into again the dummy measurement plus also some structural measurements. Then what is the battery performance or electric vehicle specific performance requirements in those test modes in NCAP and IIHS? None is explicitly defined yet today. So as an OEM, whoever is working on the vehicle design for that kind of NCAP and IIHS, which are relatively more severe crash modes compared to the regulations, they are probably internally just feeling the pressure that we must meet also the battery integrity on those more severe tests. It's normally expected that if we are designing the vehicle for occupants and other measurements, we may as well just take care of the battery integrity in those measurements as well. All right. So in summary, if I am designing a body structure, we have to take care of the front impact. And the primary measurement metric for engineers is probably the kinetic energy, half mv square. If I am looking for side impact, one impactor is coming and impacting on the vehicle, we are basically looking to the conservation of the momentum with the impactor mass, and the big M is the vehicle mass. They interact together, and the objective is the impacted vehicle will achieve a certain lateral velocity during this momentum exchange. Rear impact. Impactor is coming and impacting on the vehicle. Again, there is a momentum exchange problem, and the impactor mass and the velocity together will be interacting with the vehicle mass and achieve a forward velocity of the impacted vehicle. Even the roof crush or roof strength measurement, which is a quasi-static test, but it is also tied somehow to the mass of the vehicle multiplied by acceleration of the gravity, which is basically the weight of the vehicle, and by a factor. And as I mentioned, that factor is 3 or 4 depending on what targets you are trying to measure. In all these measurements for crashworthiness, a critical factor is the mass of the vehicle. And the general rule is higher the mass of the vehicle, more structural engineering work you have to do. Now, carrying that knowledge further to the electric vehicle design comes with certain specific challenges. In this electric vehicle design, we would like to have a larger driving range. A larger driving range means I will need a larger battery pack. And larger battery pack is basically adding to the vehicle plus the vehicle structure design. So relatively heavier EV vehicles we will have to deal with. And then the question comes, how much deformation am I allowed to say, take in the EV vehicle design in different modes? So these are the, I would say, 3 critical challenges an engineer is facing in crashworthiness design of EV vehicles. So let's go through those little more details. So here what I'm showing is the chart is the EPA miles of some of these competitor vehicles divided by the base carb weight divided by the wheelbase. Is just to approximately represent the size of the vehicle and the weight of the vehicle and how many miles it is delivering on average. And obviously, any vehicle manufacturer would always like to deliver the longest possible mileage to the customer with the lightest possible weight for the efficiency, and also a roomier vehicle for the customer to use. So what it is driving at the end is basically heavier and larger battery packs. And those battery packs are weighing more than, or the mass is over 500 kilogram. That occupies 25 or represents 25 to 30% of the vehicle carb weight. That's a pretty significant mass addition to the vehicle structure. But this is not the only part or only system that is adding mass to the vehicle of the EVs. Let's see a little bit more. Here again, I'm just citing some public domain research result here. And the comparison is ICE versus EV design. Looking at the deformation pattern in this conventional vehicle, say front impact, if there is a pole impact, there is some intrusion that is happening into the vehicle. If you're looking at the side pole impact, a conventional vehicle is taking more deformation compared to an EV vehicle. Why? I'll get to that later on. But generally, EV vehicles are heavier and they are getting designed with much stronger and stiffer structures with reduced intrusion to the vehicle body structure. Net result is EV vehicles are weighing heavier than the ICE vehicles for the same size, same configuration, etc. It's just the battery weight plus the structural configuration. And that particular research, it is basically a research, it's not a real vehicle comparison, but nonetheless they started with a conventional vehicle, they added the battery mass and they tried to add some structure for protection of it, and they came up with the conclusion that for the same configuration, same size, everything, EV vehicle is 300 kilogram heavier than the ICE vehicle. That's why there is this general drive, and many of us are aware of it, to reduce the weight of the vehicles. And here again, I'm just giving one other public domain reference information. Strategic target that research project was targeting 40 to 45% mass reduction in the standard mid-size sedan vehicle. Idea is to, can you reduce the mass in the conventional vehicle to accommodate for the additional mass that is going to come into my EV vehicle anyway and remain about the same mass, and also to deliver the competitively fuel efficient vehicle to the customers. Okay, so that's one part. We are dealing with the heavier vehicle with more structural countermeasures also needed. Now let's look into the other part of the design. This is a picture again from a public domain say published literature. It is summarizing the deformed shape or intrusion shape of the vehicle under different crush modes, like front impact, there is certain deformation happening, rear impact, certain deformation happening, side impact, certain deformation happening. And the idea is to find an area where you are going to get least amount of deformation, and can you say package your battery system in that area which is least exposed to all these impact modes, or least exposed to those say crush intrusion zones. That's the idea of this picture there. Now, if I am packaging the battery in certain areas, it is difficult or extremely difficult to really isolate it from those deformation or intrusion zones. There is going to be certain exposure in certain modes depending on how I'm packaging the vehicle battery pack. So question comes inevitably, if I am designing an electric vehicle with battery system there, how much deformation can I allow in the battery system without taking any additional risk to the safety or overall safety of the vehicle occupant and the vehicle system? That means the deformability of this battery system is coming into now the discussion here for engineers. So that's why I'm just giving it a title, Crashworthiness of Lithium-ion Battery. By crashworthiness, basically my objective here is to find out how much deformation can I allow in the battery system. Now, if I review all this different, I would say, the standards available in public domain, you will probably get a lot of information, but I am giving you a very brief high-level summary. SAE J2464. It lists those abuse tests: mechanical abuse, thermal abuse, electrical abuse for the battery systems. I'm going to just focus on the mechanical abuse, because thermal abuse, electric abuse, they have different objectives. These are very important. I'm not saying these are not important, very important, but I am going to only focus on the structural part, mechanical abuse tests. So this FCE standard, it defines a shock test, a 15 millisecond pulse of 25 G. You apply to the battery system, measure some performances to it. Then it goes to the crush test, a static crush test. Cell is compressed, as you're seeing in the picture, up to 50% of its initial dimension with a force of less than 100 kilonewton, and to verify no electrical fault or thermal runaway event to the battery system after it is compressed 50% to its initial dimension statically. It also gives the alternative way of verifying the system for a vehicle, run the FMVSS 305 test that I mentioned earlier. We know that 305 test does not say specifically what to measure in the battery in terms of the mechanical or deformability of the battery. It just talks about the electrolyte spillage and the electrical isolation, etc. So there is a big jump looking into the component level target and to the vehicle level performance, and it is hard to link one to the other. In mechanical abuse test, there are a few other things like the drop test from a 2-meter height, and also some nail penetration test with the rod, and basically punch into the battery cell and make sure it does not cause any electrical or other thermal events there. So in summary, there are pretty good severe component level tests in existence in today's industry to assess the safety and integrity of the battery system. And then we also have the vehicle crashworthiness tests that define the requirements at a very high level for the overall vehicle system. How do I connect the component level performance to the overall vehicle level performance? And here is what I find the difficulty, at least in my observation, unknown relationship between component and system level performance. Can we borrow some of the component level performance to the vehicle level, design level? Like, can I really assume that a battery system can say, undergo up to 50% of its initial deformation without getting into any kind of risk during the overall crashworthiness design of the vehicle? Is it possible or not? That's the question I'm starting with here. So we'll get to that. So before that, again, I'm just giving you one more reference, SAE JS1766, which is basically more focused on the vehicle level performance, electric vehicle level performance. But this one is basically referencing to the FMVSS 205 test modes and the requirements there. So basically, you can say these two are harmonized, this JS1766 and 205 FMVSS. There is not much discrepancy there. So concern still remains whether the tests performed at component level are comparable to those carried out at the vehicle level, or what is the link between the two? And that missing link, is there any other information available in the public domain that can bridge this gap between the component and the system? And this concern that I am just citing here, this is again coming from that reference literature. You can go and read it on your own if you're interested. Here again, I'm citing several other references for general knowledge. I don't need to go through each of them, but the bottom line message here is that there is this general understanding, or you can say general comment everywhere there, that if those lithium-ion batteries, high voltage, high energy storage battery systems are severely deformed, they can lead to some say unwanted consequences that can pose additional risk to the safety of the occupants of the vehicle. However, we don't have a way to directly measure the deformability of this, or how much deformation is happening in a battery system in a full vehicle environment, and what does it mean for the vehicle performance. So many of these references, they emotionally reflect that concern that there is a risk there, but it also doesn't give me any quantitative information what to do about it. And again, I'm just giving another page of few other information there. What it is making even more complex, that there is no one particular way that battery is being designed. There could be a pouch cell design, there could be some prismatic cell design, there could be some cylindrical cell packaged in the vehicle system there. So all these multiple design configurations are also adding more complexity to solve this engineering challenge. And for example, if I look into this particular reference literature, this was looking more into the integrity assessment for this pouch cell system. The most relevant research that I have found, and obviously there may be more, and I'd like to really learn more about these things if I can find time and if I can find more information in public domain. This paper that I am citing here, that has done quite a lot of testing work on prismatic cell to understand the overall safety of this cell at a dynamic impact scenario. And I say dynamic because if you recall what I referred to in the SAE standard, up to 50% compression of the cell for electrical and thermal integrity test, there is a quasi-static test. This particular research, it focused on the dynamic impact on the prismatic cells and trying to understand the safety of this cell. And I think this is one of the best information in my observation that I can find. So here is a pictorial description. This prismatic cell, if it is impacted in its direction, which is basically sitting on a flat plate, and you come and impact on it in this direction, and at a different rate, and they're trying to measure at what level of that deformation they saw some problems that is happening with the thermal event or electrical event, basically measuring the short circuiting in this battery system. And I can just draw a simple line here to say that when it is impacted at different rate, up to 15% of the initial dimension deformation, I'm not seeing any issues in any of the tests. So question then comes, can I define in this impact mode that up to 15% deformation I am safe for this battery system? I'm just asking a question, but I really don't have an answer to share with you. There's probably a lot more research needed to understand this one more. Now, if this battery, the same prismatic battery, instead of impacting on its flat surface, if it is being impacted in its lateral direction, the similar test, and those results are summarized by the same research paper. Now I see the margin of safety is very little. I really don't have much margin for deformability in the battery system to say, yes, integrity is still maintained up to a certain deformability, maybe 3%. So bottom line, my summary here is that more research needed to quantify how much deformation is allowed in a battery system in different impact direction to remain safe. By safe, I mean it will still not sacrifice its electrical integrity and thermal integrity after going through a certain amount of deformation. But that quantitative information, at least in public domain, is missing. Maybe certain OEMs have certain understanding from their internal research, but it's hard to find for me in the public domain to get that information. Given that no quantitative information is there in the industrial public domain landscape, then what do we know about the body structure design and the performance? And this is my last part of the discussion here to share with you. So looking into just again a side impact mode, for example, an impactor, the blue impactor coming and impacting on my green vehicle here. General approach, the way I see it, has been to maximize the body structure resistance to minimize the battery deformation. Because there is no direct quantified target available in any standard or public domain researcher. If anything there, as I say, it is probably hidden in the OEM house, because we will not be knowing it from outside whether any deformation is allowed in the battery or not. But the general tendency looks like from outside, maximize the battery structure, body structure design, minimize the battery deformation. So if we have to design to that objective, how much structural strength do I need to really plan for? And again, you can use that reference information I already mentioned earlier. Say for deformable barrier impact on the vehicle, you can look into the average pulse. If it's a conventional vehicle, you can take the conventional vehicle average pulse response multiplied by the mass of the vehicle, and you can say, I need to design it for that much of force transfer. And as I explained also earlier, through some analysis, we can even find out how much intrusion or deformation I am going to allow in the vehicle, if it's a conventional vehicle. But that's from the conventional point of view. What I already mentioned is more severe again, because it is local for side impact, is the pole impact. For pole impact is very localized in one area, so deformation is even more. So if I have to think for battery integrity, I have to think first about this very narrow impact, which is going to drive some deformation, very local way, a high deformation to the vehicle system and to the battery system. So here again, from that published literature paper, we're looking at the conventional vehicle pulses measured from these pole side impactors, those light blue curves. And this orange line I'm just drawing on top of those ones as an average among all these ones. And if I take this average one, and I can say, well, if I am designing a conventional vehicle of 2000 kilograms, so on average I will have to deliver a structural resistance of 245 kilonewton during interaction with the pole impact. Now if you compare that design against an older or earlier generation of electric vehicle Bolt that was also tested in, and the test data is available in public domain, which has been included in this literature, and that dark blue line is representing that measured response. If I look into that pulse multiplied by the approximate mass of the test vehicle, that delivered a resistance of 520 kilonewton. Is more than double of a conventional vehicle. What it means also from the deformation point of view, if I have the double integrated and calculate the dynamic intrusion for a conventional vehicle, which intrudes up to 16 inches or 400 millimeter, which is not unusual or unheard of in a conventional vehicle, in a pole impact, in the impact area, pretty good amount of deformation happens, which is shown here with the measurement. Compared to that, to the electric vehicle measurement here, that has a reduction of about 6 inches of intrusion. Now, is it driven by the occupant safety? Maybe part of it, that I don't know, but obviously the protection of the battery system played a critical role there. Limit the intrusion to the vehicle system, because we do not know how much deformation we can take into the battery. Or maybe we know, but it is a very limited amount, not too much. Battery system probably cannot live up to that 400 or 16 inches of deformation happening into the vehicle system. So it tells that the battery system is limiting how much deformation we can take into the body structure. That means body structure needs to be much stronger to protect the battery system, and with that the whole vehicle system. Okay, just to show you visually what it means, taking some pictures from YouTube of a pole impact test of a vehicle. This is the impending state when the pole is touching on the vehicle and the door. And at the maximum intrusion level, pole is basically coming and stopping at the A-pillar area. Obviously, door and things already got deformed, which is what we showed in the previous page measurement. Probably up to a certain amount of deformation is happening in that measurement. Beyond that, at the structural level, we are not seeing any more intrusion. So in summary, what it means that the structural design is being developed at a much higher strength level for the EV vehicles. And EV vehicles are heavier, so that is adding even more structural countermeasures into the body structure compared to a conventional vehicle. If we had known that certain amount of deformation or a large amount of deformation is allowable in this say high voltage batteries, probably the overall system could be designed in a little more relaxed way. But current state of the knowledge is design the structure to the maximum capacity, minimize the battery deformation. What do you know so far from the limited field data, that how this design has been doing in the field? That was also one of my personal curiosity. And I could find one very good paper published in January 2020. And that paper tries to summarize many of the field incidences that are available in different parts of the world. And I'm just copying few words from that publication. Obviously, if you are interested, you can read this whole paper. In general, most of the EV fire accidents are caused by the thermal runaway of lithium-ion battery. The common causes of those fire incidences include self-ignition or spontaneous auto-ignition in parked vehicles due to arson or sustained abuse. So generally it is saying, it is not really listing crash as an event leading to those fire incidents in most cases. The paper goes on to summarize even more. It says, with modern design of lithium-ion batteries in EV, the large majority of the crashes will not cause harm to the battery. As an engineer and as a customer, I felt pretty secured in my mind that, okay, the design practice that is there in today's vehicle is doing good. Yes, maybe there are a few incidences where the fire is appearing in certain vehicles after a crash event, but at least this paper is giving me some comfort mentally that many other fire incidences with EV vehicles that we read about in newspapers and in media publications, many of these or most of these are non-crash events. And most of the vehicles, at least the paper is claiming, will not cause harm to the battery and hopefully will not cause harm to the occupants. But that's again the conclusion of the paper. It's not my conclusion or even an OEM conclusion or even a government agency conclusion. But nonetheless, at least that information is there in the public domain for me as a customer to feel safe about electric vehicles. And that's the end of my presentation here. Thank you for listening.